Hello there, it's me. I'm currently riding a bike, and I figured that since I don't have any podcasts to listen to, I figured that I might as well, make something while doing this. So let's talk about quantum physics. Now, you may be confused, thinking, why on this earth would I ever talk about such a topic? Well, for a simple reason. I really like quantum physics. To put it simply, I love pretty much anything involving science. And I figured that I might as well talk about some stuff because I have 15, 20 minutes before I'm going to be done with this and go around the loop, so thought I might as well do something while doing this. So one thing about quantum physics is imagine it like this is a concept of quantum physics. Imagine you have a set of two particles. They're paired together, and you had them across the universe in two different areas. Well, one of those particles would always be positioned as up, and one of them would be positioned as down. Though the problem is, you don't know which one's up or down until you observe them. But the issue with that is, if you have it, say, 2 light years away, and you observe one 2 light years away, and observe one here on Earth, they will always have one be the top and one be the bottom. And you'd think, how is that possible? You can't have information travel faster than light, can you? Well, there's a simple answer for that. Nobody knows. Nobody really understands why physics are structured in such a way, but it always is a thing that when you observe a particle, one will be up and the other would be down. It just is the kind of thing that would be, that's just how it works. There isn't exactly a huge thing as to why, but it kind of just is set up that way. It's like one of the things, it's like the odds happen to be aligned to where that's the case. Oh gosh, I just ran over a snail. Anyway, one other thing about quantum physics is some of the particles, they're pretty cool, I'll say that as much. Here's an example. I'll talk about some of my favorite particles, which are known as quarks. And quarks they're pretty cool. You see, you have atoms, which are made up of protons, electrons, and neutrons. But the thing is that what makes up the protons and the neutrons at the center? Well, that's what the quarks do. You have 6 different kinds of quarks. You have top, bottom, up, down, charm, and strange. And the cool thing about those is that you have pretty much the top and bottom quarks that I believe is actually up and down quarks. It's one of those two. I can't think of it off the top of my head, but either the top, bottom, or the up and down ones, they're responsible for making matter. And when making matter, you have to have a certain type of quark because that's the building blocks of protons and neutrons. As they're the building blocks of atoms, so are quarks to protons and neutrons. The other 4 quarks you can kind of think of as the radioactive elements on the periodic table. You have them with half-lives, where eventually you'll have them decaying into some other element. Well, quarks are kind of like that, but they have a really short time to live, where a strange quark, for example, will decay really quickly into a different kind of quark until it eventually gets down to the more stable top or bottom ones, or up and down. It's one of the two, as said. I forgot which ones do that, but it's either top, bottom, up, or down. Strange and charm are completely different things. Now, the thing about quantum physics is that there's actually a part of it that says there can be a thing called a superposition, where if you were to have a particle and you didn't observe it, you would have to assume that the particle is in both positions, either up or down, because you don't know which one it is yet. Until you observe it, you never know the true answer. And one experiment, or not really experiment, but rather a thought experiment to prove this, is Schrodinger's cat, where imagine you have a box that you place a cat in and a bowl of poison. And you leave the cat for about, a day. And then when you come back the next day, assuming the cat, already had food and water beforehand, so there's either a chance it's going to be alive or dead. Because you could assume the cat would eat the poison, assuming it doesn't know, of course, then you can't tell until you open the box whether the cat will be alive or dead or not. So the cat is in a superposition of being both alive and dead at the same time. Not physically, but theoretically, because you don't know yet. You see this? What? What are you all doing here? I'm just baffled. Don't kill me now, okay? I just want to ride by, alright? I know you guys eat dead bodies, and I know that you probably have the ability to kill me, so let's just leave it at this, okay? All right, cool. Anyway, back into particles and dead cats. There is one thing on the topic of particles is there is a thing that is one of my favorite things just in the entire world called the LHC, or the Large Hadron Collider, and it's located up in Switzerland, and it's a 27-kilometer loop of just machinery beneath the ground, and it is probably one of the biggest machines ever devised and created. It might actually be the largest, I'm not really sure, but it's massive, and it is, well, it's in the name. It's a particle collider. Now, the cool thing about this collider, in my opinion, is that it is just absolutely incredible, because it's such a large machine with the sole purpose of colliding protons and different other kinds of, elementary particles together to create new things. And the collider has been really helpful in, science and everything, because it's done a lot of discoveries in terms of different particles and everything. Like, they discovered one called the Higgs boson, which they call the God particle, because it's partially responsible for giving things mass, or rather, it's part of the Higgs field, which is a field propagating throughout the universe, but it's more like a citation in the Higgs field, so they call it the God particle because it correlates with the Higgs field. Regardless, though, the power of the machine is just unmatched by most things. It is ridiculous, because the amount of power that you would use to make that machine work for couple seconds, I believe it's around the equivalent of taking a train and accelerating it to 100 miles per hour. All the energy that train has is equivalent to around a couple seconds of that machine being on. Another cool thing about the machine is that it actually has the capability of creating tiny black holes, because the amount of energy in the little beams of protons that they fire is so great that actually the collision is, because the collision is a couple miles per hour less than the speed of light, which is around 299,700,000 meters per second, around 186,000 miles per hour. And the collider manages to accelerate particles to the speed that's probably 10 miles per hour less than that. So with that much energy being put into such a small area, and with particles moving that fast, because particles with mass typically don't ever move that fast, there isn't enough energy in the known universe to accelerate a single electron to the speed of light. So the thing with that is that it's exponential growth, kind of like how you have decibels, where 1 decibel is 10 times louder than the previous decibel. So it's a pretty strong machine. Anyway, I digress. The machine can create black holes via the mobility, where it speeds up the particles and they collide, causing such a massive release of energy that it kind of just collapses in on itself and makes a tiny black hole. But they're so small, and the Hawking radiation from them disperses so quickly that they're pretty much non-existent, because they just are, really, really quick to go away. Although the collider actually does have the ability to create another thing that I really like called antimatter, which is basically the same as regular matter, except it's just the opposite charge of the particles. So you have the electron inside the antimatter is actually called a positron, and the other particles that make up it just have the opposite electric charge. So it's the same thing as regular matter, except when you touch regular matter to antimatter, it annihilates itself in a massive explosion. For context of how much energy comes out of that explosion, I believe 1 kilogram of antimatter has around the equivalent energy of the Tsar Bomba, which was the largest nuclear bomb ever detonated somewhere. So that's pretty cool. The only issue about creating antimatter is that it's really hard to keep, because it's really hard to preserve, because the thing is, you can't have it collide with regular matter, which includes air and literally any material that you build anything with. So the scientists have to get creative, and they take really, really strong magnets, which also accelerate the particles to, near light speeds, but they take different magnets and they kind of suspend them in a bathtub-shaped magnetic field, which lifts up the particles and kind of holds them in a cradle so that they don't touch anything and explode. The thing is, though, is that it's really hard to make a lot of it because they make it pretty much atom by atom. So it's like they've only created a few, I think, nanograms of antimatter, which isn't even enough to boil water in a small amount. So, it's not that much. Anyway, I'm now returning home. So hopefully you learned something. Maybe I said some stuff wrong. I probably did. But to be fair, I'm half focused on moving. You know what, though? Yeah, I hope that something was learned from that. Have a good night.